Swayam Prabha. Digital India. Educated India.
So, welcome to the 7th lecture on time series modeling and forecasting. In this lecture, I am going to discuss different methods for smoothing and adaptive forecasting. As we have already discussed in several previous lectures, the method of moving averages can be used for different purposes. Say for example, you can use a method of moving averages for the determination of trend component. It is also used in obtaining the seasonal indices. Now, what we mean by the moving averages? Moving averages are actually rolling averages. Say we start from the first observation, take average of say first k observations, then we leave the first observation, we start from the second observation, go up to the k plus 1th observation, take average and so on. So, this is some kind of rolling average, and this moving average helps us in smoothing the series. In the last lecture, we also saw that how moving averages smooth the irregular component or random component. The variance of the random component after taking the moving average reduces. So, the series becomes more smooth. In fact, the moving averages is smooth the shorter variations or the periodicities or variations of shorter duration at the cost of longer ones, and they retain the longer ones. So, this is a specific purpose of moving averages, smoothing the series. So far, we have considered the moving average with equal weights, but it may be possible to assign different weights to different moving averages. So, you may have weighted averages, and obviously, in weighted averages you should assign more weightage to more recent observation. So, let us consider the use of such kind of weighted averages in smoothing the series and in forecasting the series. We consider the exponential smoothing, exponentially weighted moving average to smooth a time series. Basically, what we do in the exponentially weighted moving average technique, we use the weights which are exponentially decreasing. This is actually a class of procedures for smoothing discrete time series. You can even apply it in signal processing as low pass filters to remove high frequency noise. Then simple moving averages, as I told you earlier, use equal weights. Exponential smoothing uses exponentially decreasing weights over time. So, this is the specialty of exponentially weighted moving averages. It does not require any minimum number of observations before starting exponential smoothing. You remember that for simple smoothing or for simple moving averages, you require a minimum number of observations. Suppose you want a moving average of period k, then you should have at least k plus 1 or k plus 2 observations, at least more than k observations. Otherwise, it won't be possible for you to apply the moving averages. But here you don't impose any such kind of condition on the number of observations. Now, suppose y t is a time series, t varies from 0 to n, and y naught is the initial value of y t. Now, we define a new time series S t, and this S t is actually a smoothed version of y t. We take S naught equal to y naught, and S t is equal to alpha y t plus 1 minus alpha S t minus 1. Here this alpha is called the smoothing factor, and it lies between 0 and 1. So, in this method, what you are actually doing, this S t minus 1 is the smoothed value for the previous period, for the period t minus 1, and this y t is the current observation of the time series, and then you have taken a weighted average of these two, alpha y t plus 1 minus alpha S t minus 1. So, this is actually a weighted average of current value of the time series y t and one period lagged value of the smoothed series. Then the smaller the weight alpha, the less influence each point has on the smoothed time series. Here I have plotted as time series. This one is the original time series, then first we have taken exponentially weighted moving average with alpha equal to 0.5. So, you get this series alpha equal to 0.5, and then for alpha equal to 0.05 you get this series. So, you observe that the series becomes more smooth if you take a smaller value of alpha. The smoothed series with alpha equal to 0.05 is much more smoother than the series with alpha equal to 0.5. But if you decrease the value of alpha, then the smaller the weight alpha, the less influence each point has on the smoothed time series. So, the weight of y t decreases. Its role in defining S t decreases. This formulation is also known as the Brown's simple exponential smoothing procedure. S t is also known as the smoothed statistic, and it is as I told you earlier, simple weighted average of y t and the previous smoothed statistic S t minus 1, and larger values of alpha reduce the level of smoothing and give greater weight to recent changes in the data. So, if you increase the value of alpha, the recent changes in the data, the recent changes in the time series get more weightage. But a smoothing procedure gets distorted. The resulting series will be less smooth. For instance, if you take the extreme case alpha equal to 1, then your output series is st equal to yt, which is the original time series. So, there is no smoothing for alpha equal to 1. On the other hand, if you take alpha close to 0, then it has a greater smoothing effect. But the smoothed series are less responsive to recent changes. The role of current observation yt decreases in defining st. We can use this approach for forecasting purpose also. So, now we come to adaptive forecasting using exponentially weighted moving average. So, we construct the forecast using exponentially weighted average of past observations. Obviously, more recent values have greater influence on the forecast, and exponentially decay of influence of the past data. So, the influence of the past data decreases exponentially, and it is something which our common sense also says. While making forecast, your more recent values should get more weightage, because those values have more information about the future values in comparison to past data. So, this makes sense. This method is quite simple, it is computationally efficient, it is its ease to adjusting to changes of the process being forecast with reasonable accuracy make it very popular. So, you can use this procedure for forecasting a time series successfully. It also allows to determine the influence of recent observation on the forecast value. You know the weight of the recent observation. So, how much the recent observation is influencing the forecast, this is also known. Again, you have n observations of the time series, and we assume that there is neither cyclic variation nor pronounced trend. So, this is the basic assumption that cyclic variation is absent and there is no trend, or even if there is some trend, it is negligible. So, this procedure is based on these two assumptions. Then exponential smoothing equation is y hat t plus 1 is equal to alpha y t plus 1 minus alpha y hat t. So, in place of s t minus 1, you have y hat t, and in place of s t, you have y hat t plus 1. So, y hat t is the forecasted value at time t, alpha is the smoothing constant, and alpha lies between 0 and 1. So, the procedure is very simple. You are adjusting the last predicted value of y, say y hat t, by taking into account the most recent observation, and then your forecasted value y hat t plus 1 is the weighted average of y t and y hat t. So, this is how recursively you can obtain different forecast values of y t or forecast values of y t for different values of t recursively. Usually the initial forecast value y hat 1 is unknown. Then one of the option is that you set the first estimate y hat 1 equal to y 1. So, the initial forecasted value y hat 1 is equal to y 1, but the problem with this approach is that the initial value y 1 will have an unreasonably large effect on early forecasts. A better option is you take average of first few observations. Usually we take average of 10 or more observations, or if your time series is not very long, you can take average of first 6 observations, and then use the average of first few observations for the initial smoothed value. So, you replace this y 1 hat by the average of first few time series observations. Now, we can write y hat t plus 1 minus y t equal to y hat t plus 1 is equal to alpha y t plus 1 minus alpha y hat t. So, y hat t plus 1 minus y t is equal to, you subtract y t from here. So, you get minus 1 minus alpha y t plus 1 minus alpha y t hat, which is equal to 1 minus alpha y t hat minus y t. And suppose E t is equal to y t hat minus y t, which is the forecast error at time t, then this is equal to 1 minus alpha into E t. Then by recursive substitution, y hat t plus 1 is equal to alpha y t plus 1 minus alpha y hat t. In the next step, we write y hat t equal to alpha y t minus 1 plus 1 minus alpha y hat t minus 1. So, what you get? Alpha y t plus 1 minus alpha into alpha y t minus 1 plus 1 minus alpha square y hat t minus 1. Again, in the next step, we substitute y hat t equal to alpha y t minus 1 plus 1 minus alpha y hat t minus 1 here. Then you will obtain the next step as alpha y t plus 1 minus alpha into alpha y t minus 1 plus 1 minus alpha square into alpha y t minus 2 plus 1 minus alpha cube into y hat t minus 2 and so on. You proceed recursively. At last you get this expression alpha y t plus alpha into 1 minus alpha y t minus 1 plus so on plus alpha into 1 minus alpha to the power t minus 1 y 1. So, you can write the forecast equation as y hat t plus 1 equal to alpha. You can take alpha outside the summation sign and then summation j equal to 0 to t minus 1 minus alpha to the power j y t minus j. For j equal to 0 you get this term, for j equal to 1 you get this term and so on. For j equal to t minus 1 you get the last term. Y hat t plus 1 is then the weighted moving average of all past observations. Again you look at this expression. Now, alpha lies between 0 and 1. So, 1 minus alpha also lies between 0 and 1. So, as j increases, 1 minus alpha to the power j decreases. So, the most recent observation is for j equal to 0 gets the maximum weightage in this forecasted value, and that means if you take j equal to t minus 1, the first value y 1 gets weight 1 minus alpha to the power t minus 1, the minimum weightage. So, the series of weights decline towards 0 in an exponential fashion. It is a exponentially decreasing series. Then as we go back in the series, each value has a smaller weight in terms of its effect on the forecast. So, more recent values are getting more weightage and past values are getting less weightage. Now, if alpha is close to 0, this allows the distant past observations to have a large influence. Again we look at the expression. If alpha is close to 0 means 1 minus alpha is close to 1. So, with increasing j, 1 minus alpha to the power j is not going to decrease very fast. So, the past values are also getting larger weightage. If alpha is close to 1, then the past observations have a negligible influence. So, again you look at the expression, if alpha is close to 1 means 1 minus alpha is close to 0. So, this 1 minus alpha to the power j decreases very fast with increasing j. So, the past observations get very small weightage or negligible weightage. So, those observations have a negligible influence on the forecast. The problem is how to select alpha. you must require some criterion to select the value of alpha, appropriate value of alpha. So, we consider some methods for measuring the accuracy of forecast values. The first measure is mean absolute percentage error, MAPE. Now, forecast error is ET equal to y hat t minus y t. So, we take absolute value of E t divided by y t and multiply it by 100. So, what you get? Absolute percentage of error, means absolute percentage of error with respect to y t, and then you take mean of these absolute percentage of error. So, you take summation from t equal to 1 to n and divide it by n. So, you get mean absolute percentage error. So, this is a measure of accuracy of forecast, and lower the MAPE, the better is the forecast. Usually MAPE below 10% is highly accurate forecast. It is considered as highly accurate forecast. A MAPE between 11% to 20%, this is just a general criterion. It is a good forecast. Then MAPE between 21% to 50%, it is an indication of reasonable forecast, and MAPE above 50% is an indication of inaccurate forecast. Two more measures are mean square error and root mean square error. We define mean square error as 1 upon n summation t equal to 1 to n E t square. So, this is simply the sum of squares of errors divided by the number of observations, and root mean square error is square root of MSE. These two measures, MSE or root mean square error, RMSE, can be used as criterion for selecting smoothing constant alpha. In practice, what we do, we obtain the forecasted values for the different values of alpha. We assign values from 0.1 to 0.99 to alpha, or you may even start from 0.01 to point and go up to 0.99 and select the value with smallest MSE or root mean squared error. So, this is how you can proceed. Double exponential smoothing, or this is also called Halt's method. Now, remember that in exponential smoothing procedure, in simple exponential smoothing procedure, which we have discussed before, we have assumed that there is no trend and no seasonal pattern. Now, in this method, we relax the assumption of no trend. So, this method is used for forecasting the time series when the data has a linear trend and no seasonal pattern. So, still we are assuming that the time series does not have any seasonality, but it has linear trend. This method is also called the Halt's trend corrected or second order exponential smoothing procedure. Then we introduce a term to take care of trend present in the time series. This method is also capable of capturing increase or decrease in linear trend. So, you can use it for increasing trend as well as for decreasing trend also. These are the steps for this procedure. We start from t equal to 0 and then you set S naught equal to Y naught. Then here actually apart from alpha, we are introducing another parameter B, and this parameter B varies with T, it depends on T, and actually Bt is the best estimate of trend at time T. So, we start with initial value of B naught equal to y 1 minus y naught, or sometimes you take B naught equal to y n minus y naught upon n. So, basically we are assuming that the trend is linear. So, y n minus y naught by n gives you the rate of change in y's per unit observation, you can say. When you move from t to t plus 1, this is actually the rate of change in y's, or average rate of change in y's. For t greater than 0, we define S t equal to alpha y t plus 1 minus alpha S t minus 1 plus B t minus 1. This term B t minus 1 takes care of the trend. Similarly, we take B t equal to beta S t minus 1 plus 1 minus beta B t minus 1. So, this beta is the trend smoothing factor. So, here you have two smoothing factors, alpha and beta. The role of alpha is to smooth the series, taking care of taking care of the trend component also, and the role of beta is in smoothing the trend component. For forecasting beyond y t, you have y hat t plus k equal to S t plus k times B t. Now, this term is because of trend. So, you are adjusting the forecast for trend. Still in this procedure, we are assuming no seasonality, but sometimes in the time series you may have seasonality. So, you must have some procedure for forecasting which takes care of seasonality also. We will come to this point later on. Then Brown's linear exponential smoothing or double exponential smoothing procedure. This uses two different smoothed series that are centered at different points in time. And then forecasting formula is based on an extrapolation of a line through the two centers. So, these are the steps for the Brown's smoothing procedure. Initially, you set S naught dash equal to y naught, S naught double dash equal to y naught. So, actually that is why I said that the forecasting formula is based on an extrapolation and a line through the two centers, and this procedure uses two different smoothed series that are centered at different points in time. You have two smoothed series, S naught dash and S naught double dash. Then S t dash is equal to alpha y t plus 1 minus alpha S t minus 1 dash, and for the second series S t double dash is equal to alpha S t dash plus 1 minus alpha S t minus 1 double dash. So, here you have smoothed the series y t using this equation. This leads to S t dash, and then you further smooth S t dash using this equation. So, this leads to S t double dash. Then y hat t plus k is equal to A t plus k B t, where A t is the estimated level at time t. So, actually A t is equal to 2 S t dash minus S t double dash, and B t is the estimated trend at time t. So, B t is equal to alpha upon 1 minus alpha S t dash minus S t double dash. So, still means this procedure also does not take care of the seasonality component. Now, if your time series has both trend and seasonal components, then you should go for triple exponential smoothing or Halt-Winters smoothing procedure. So, we apply this procedure when your time series has both seasonal component as well as trend component. Again, we have a sequence of observations beginning at time t equal to 0. L is the length of the cycle of seasonal change. We assume that this length of the cycle of seasonal change is known, L is known. It may be a quarter or it may be a month. Then N is the number of complete cycles. Then we consider two different cases of seasonality, when the seasonality is multiplicative and when the seasonality is additive. Now, suppose L is the length of the cycle and capital N is the number of complete cycles, then how many observations you have? Small n is equal to capital N into L. This is the total number of observations. So, we arrange the observations in such kind of table. Here you have different periods of seasonality, means suppose you have quarterly data, then capital L is equal to 4 and you have 1, 2, 3, 4 here. If you have monthly data, your seasonality is monthly, then you have 12 months here, and capital N number of cycles which you have. So, if you have data for 10 years and quarterly data for 10 years, then on this side you will have 4 rows in the table, and here you will have, so suppose you have 10 years data, then 10 columns. Then you take C I naught equal to 1 upon n summation j equal to 1 to n y L j minus 1 plus I upon A j, and A j is equal to 1 upon L summation I equal to 1 to L y L j minus 1 plus I. So, basically A1 is the arithmetic mean of this first column, means suppose here you have different years, then A1 is the mean for first year, A2 is the mean corresponding to this column, and so on. And similarly, you define CIs, CI naught here. You divide each observation by the mean of that column to which that observation belongs, and then you take the arithmetic mean of those quantities. So, Ci naught is the initial estimate of seasonal indices, and Aj is the average values of y's in the jth cycle. Then initial trend estimate B is B naught equal to 1 upon L y L plus 1 minus y 1 upon L, means this minus this upon L plus y L plus 2 minus y 2 upon L, this minus this upon L, and so on. You go up to y 2 L minus y L upon L. So, this is the initial trend estimate, this is the initial estimate of B. Then ST is the smoothest statistic, L is the smoothing factor of data, BT is the best estimate of a trend at time t, beta is the trend smoothing factor. So, beta also lies between 0 and 1, CT is the sequence of seasonal correction factor at time t, and gamma is the seasonal change smoothing factor. So, gamma also lies between 0 and 1. Then this is the algorithm for triple exponential smoothing formula, smoothing. So, here I have given the formula for multiplicative seasonality. S naught is equal to y naught, then you define S t equal to alpha y t upon C t minus L plus 1 minus alpha S t minus 1 plus B t minus 1. Similarly, you update the trend component B t using this formula, B t equal to beta S t minus 1 plus 1 minus beta B t minus 1. You update C t using this formula, gamma y t upon S t plus 1 minus gamma C t minus L, and then this is the forecasted value, y hat t plus k is equal to S t plus k B t C t minus L plus 1 plus k minus 1 mod L, where actually A mod n is defined as the remainder of division of A by n. A and n are positive numbers. So, this is the formula for triple exponential smoothing. You are updating the series, the trend component, the seasonal component, and then you are updating the forecast values. You are obtaining the forecast values. Then this is the formula for additive seasonality. So, in the multiplicative seasonality, we have divided y t by C t minus L, or in this equation we have divided y t by S t, because you are assuming that the seasonality is multiplicative. But if you assume additive seasonality, then you have to subtract the seasonal part. Rest of the terms are the same. So, now I have given a simple example which I have done using the software R. We have Google stock data set with 1000 observations, and we have divided the observations into two parts. First 950 observations on which I have fitted the procedure. So, this is also called the training set, and then remaining 50 observations belong to the test set, means for checking the accuracy of the forecast. So, actually I have divided the observations into two parts, 950 and 50. On 950 observations, I am going to fit different exponential smoothing procedures to obtain the forecasted values. And since you know the remaining 50 observations, you can easily check how much accurate your forecast is. So, first I have applied the simple exponential smoothing procedure. Now, this is the time series and this part gives you the forecasted value. So, what kind of forecast you get? You get a flat lined estimate. So, a flat lined estimate is projected by simple exponential smoothing. And the reason is that this procedure is not capturing the trend present in the data. So, after this point it is projecting a simple flat lined estimate for all the 50 observations. Then we have tried to remove the trend and do the forecasting again. So, we removed the trend component by differencing the series and used simple exponential smoothing. And well, in both the cases I have used software to select the best alpha value. So, the best alpha value is selected automatically. So, you get these forecasts. But since the data set was differenced, the procedure is forecasting differenced values. This procedure is not forecasting the exact values, this procedure is forecasting the differenced values. Then I have used halt method for forecasting purpose. So, halt method assumes that the time series has trend, but it does not take care of any seasonality present in the data. Again, the best possible values of alpha and beta are selected automatically. So, here you get the forecasted values. These are the forecasted values. So, at least you are getting some better forecasts, because you are taking care of this linear trend present in the data set. Now, before going for the Holt-Winters seasonal method, first I have tried to check whether the time series actually has seasonality or not. So, using the R software, I have decomposed the time series for 4 components. So, this is the actual data set. Then these are the trend values, almost linear. Then you get the seasonal pattern also in the data, and this is of course the remainder term. So, from this graph you can easily check that the time series has seasonality. It is very clear. So, one should go for the Holt-Winters method for forecasting purpose. Then we have used the Holt-Winters method and we get these forecasted values given in this region. Now, these forecasted values take care of the seasonality. So, that is why you are getting better forecasts. Well, here I have not reported the mean squared error or root mean squared errors of the forecasts, but this procedure provides the best forecasts. And the reason is that the data actually has seasonality in first two, it has trend also. So, in simple exponential smoothing procedure, when you are applying the simple exponential smoothing procedure, it does not take care of trend as well as seasonality. So, you get the worst forecasts, you get just flat forecasts. In the second procedure, since you are taking care of the trend component, you are in a better position, you get slightly better forecasts, but still there is possibility of improvement. So, then we have checked whether the time series actually has seasonality or not. For that purpose, we have decomposed the time series into into the three components. We check whether the time series has trend component or not, or the seasonal component or not, and then the graph clearly shows that the time series has both trend as well as seasonal variations. So, then we have applied the third procedure and we get the best forecast here. We have also checked the influence of gamma on root mean squared error, means we have forecasted the values of y t for different values of gamma, and then we plotted the root mean squared error here, and then you can easily verify that for gamma equal to 0.21, you get the best forecast. So, this exponentially weighted moving average procedures provides you a good alternative for forecasting the values of y t's when you have no seasonality or trend component in the time series. You can apply this procedure when the time series has trend component as well as seasonality or only trend component. One more thing you must have noticed that for the applying the procedure, I have divided the entire time series into two parts. First 950 observations and remaining 50 observations. Well, you can try some other combination also. You can take 900 observations for fitting the procedure for obtaining the forecasts, and remaining 100 observations for checking how accurate your forecast is. In fact, this procedure is called the cross validation. You divide the entire sample period into two parts. On first part, you apply your procedure or you fit your model, and on the second part of the sample, you already have the values of the random variable or values of the time series y t's, and then you apply the model or procedure for forecasting purpose, and then you can easily check how accurate your forecasts are or how good your procedure is. So, this technique is called the cross validation, and you can apply it in fitting any other model also. So, okay. So, I think I should stop here. Thank you very much.
am Professor A.K. Sharma and I teach sociology in IIT Kanpur. I am taking up a question, what is world population crisis? World population crisis refers to explosive growth of population which occurred during 1950s and 1960s. For millions of years, some people estimate that perhaps man appeared on this planet Earth 5 lakhs years ago. It took these 5 lakhs years for world population to reach first billion in 1820 AD, and that means that the population in ancient times must have been rising at rate 0.000 something percent per year. Now, in 1950s and 1960s in the world, you find that population started growing at rate more than 2% per year. This is what is meant by population crisis. You can imagine that if a population grows or anything grows at 2% per year, then in about 35 years time it can double. And obviously, particularly in the context of less developed countries, it had implications for poverty removal, for employment generation, for maintaining health, improving life expectancy, raising educational levels, etc., etc. The reason behind this population crisis was improvement in life expectancy or improvement in general health standards of populations. You may not be knowing, or you will be surprised to know that about 100 years ago in our country, life expectancy means average age of death or average age of life, whatever you say, of a newly born child was only 20 years, and today it has reached the level of 68 years. Much of this improvement in less developed countries occurred in 1950s and 60s, and therefore, with improvement in health, improvement in life expectancy or average age of birth, average age of death, population started growing at explosive rates, and people started writing about this. This is population explosion, or this is population crisis. And now one can say that the period of peak growth rate is over, and from 1971 onwards in the world as well as in our country, growth rate of population has started declining. Now, in India, you may like to know what is the current growth rate of India's population. Currently, India's population is growing at 1.5% per year, and the reason is that after sudden or unexpected improvement in health conditions in 50s and 60s, which led to population crisis, we find that today average number of children has also started coming down. So, there was a time when average number of children per woman was around 11 or 12, now it has come down to 2.5, and therefore, the growth rate of India's population has come down to 1.5%, and we can hope that in the future, means in the coming decades, even if nothing changes on the front of fertility or number of children, India's growth rate of population will decrease further and eventually come to a zero level, as said by the 11th 5-year plan of India. And now the major cause of high growth rate of population is not high fertility, but the age distribution of population. So, we have a high percentage of population at the younger ages, and that is the cause of high rate of growth of population. Eventually, when population of India will also age like population of other developed countries, our growth rate will start falling. Thank you. Now, we will meet in the future.